Hey everybody, the purpose of this video is to go through the video analysis portion of your first experiment, which is called the Saintly Produce Plunge. Yeah, I know it's kind of a cheeky title. Now to do this, we are going to start at the beginning, which of course is going to be our Canvas webpage. What we want to do is go into Assignments, go to Experiment 1, and I assume that you've already done this experiment, and we want to look at the write-up. It doesn't matter which one we look at. Either one will be just fine. I'm going to click on the Word document, and this of course is the write-up for the experiment, and I am going to be focusing on Part B. Now in Part B we have this link, and this will be your link to the video analysis software. You can click either this link right here or this. They could take you to the exact same spot, which happens to be here. And this is the software that we're going to be dealing with. Now, you will have received an email. I know the experiment is scheduled for Monday. You should be getting an email on Tuesday or Wednesday, or possibly Thursday. And once you receive that email, you're going to want the email will either have an attachment to a video or a link where you can download the video. And once you have that on your computer, you can import it. And you can do that by clicking Import Video here. And the video that I want to play with is this video right here, where with the help of my daughter, I am dropping a small white soccer ball. Okay, so here's my video. And this, of course, is the software. Now, notice at the bottom we have a couple of features here. We can actually play our video. We can stop it. We can back it up. And then these buttons right here allow you to move the video up frame by frame and back frame by frame. Okay. Over here we have this thing called Add, which is what we're going to do. Is we are going to add dots, which is going to create for us a motion diagram. We can edit those dots, and we are also going to, and we can use this to set up our coordinate system. Let's first go ahead and do it, and we can and zoom up to where the motion begins, and we can use this dot right here to make that happen. I'm going to zoom it to just the point where I let go, right about there, and I'm going to back it up frame by frame until I get to the point where I want to start, which will be right there. Now, as I mentioned before, we have to have a coordinate system. Okay, we need to decide what's going to be 0 and what is going to be the positive direction. And to do that, we want to click on System, and let's go ahead and click on Origin. Now, I want my origin to be where the ball is. Of course, there's a problem there because this ball is being hidden by this thing called Cartesian, but I can fix that. And I can fix that by essentially zooming in. How do you zoom in, you ask? Well, you can use the scroll wheel on your cursor to do that, on your mouse cursor, on the scroll wheel on your mouse to do that. Okay, and so you can use that to zoom in and out. And then you can use your Shift button and your left mouse button to zoom up and down. So basically hit Shift, click on your left mouse button, and you can zoom up and down. Now the first thing I need to do is to get this origin up to where the ball is. So I can move it there, then I can pan, I can move it some more, I can pan some more, and I want that right there, right basically on the middle of the ball. And the other thing that I want is I want this right here to be the positive Y direction. So I'm going to rotate my axis until the Y is pointing down. Okay, to see if it looks sense, what we can do is just zoom back out. Man, it looks about right. Okay, so now my Y is going to be in the positive directions. Now the other thing we need to do is we need to come up with a scale, because remember, this is an image. An image is scaled in pixels, which is pretty much what we have here. We want to map pixels to distance. Now one of the things that we did during the lab was we measured the distance from the bottom of the second rail to the top of the third rail, and we can actually use that to actually come up with our scale. So we're going to click Scale. Okay, and I'm going to have to zoom back out again, and because I need to get this up to where we're going to be. Now I can zoom back in, pan up. I can put one end right there. That's where we actually started our measurement. And the other end right here. That is actually where we completed our measurement. Just scoot that over, just scoot that over a little bit. And notice how I'm kind of all set so I can see where the lines are. Okay, and we have that over there. And remember, we measured this to be 4.21 meters. So that basically, I'm going to put in 4.21, and this tells us that tells the analysis software that, well, 838 pixels is pretty much 4.21 meters. Hit enter to make sure it takes, and there we are. Okay. Now what we're going to do with this software is create this thing called a motion diagram. We are going to take samples of the ball's position for a fixed time intervals. What are those time intervals going to be? Well, you can figure that out by coming down to advanced video options. We are going to basically compute the position for every single frame. And we have a frame rate of 59.95 seconds, just about 60 frames per second. So each frame is going to be about 1/60th per second. Okay, now to do this, we are going to click Add. And that's what I'm looking for. And I'm already at the start of the motion, so I'm going to come over here and I'm going to kind of like pick a specific point on the ball, maybe the top edge of it, and I am going to click it. Once I do, it creates a point and advances exactly one frame. Now, as you can see, didn't move much. Okay, so I'm going to go ahead and click it again, and it keeps on advancing. I'm going to do this, and at some point you can see me letting go, and the ball is beginning to drop, and I'm going to do my best to follow it. Now, at this point, it's going to be kind of hard because the ball's not really moving all that much, so it's almost like I'm clicking almost the exact same space. But remember, as the ball begins to accelerate, the dots will become farther and farther apart. And as you can see, now the ball is really beginning to move, and it's somewhat easier to do. And yes, this is what you are going to have to do. Okay, so just bear with me while I continue to do this, and I'll be back with you in a couple of seconds. Okay, I'm back for just a little while. Now you'll notice the ball's off the screen. What can we do here? Well, now what we can do to fix this, what we can do is just go ahead, pan on down. Up there's the ball, and there's the bottom. Now what I'm going to do is I'm going to continue clicking the ball until the ball is just above the bottom, or just above the ground. The frame where the ball is actually touching the ground, I'm not going to include because I don't know if the ball is, because at that particular point the free fall is over and the interaction of the ground takes over and the motion changes. So I'm just about there, so just bear with me while I finish this up. Okay, now that I'm this close, I'm going to check my frames just to see what's going on here. So that frame, we're getting about to the bottom. If I go one step forward, we're making contact, and the next frame after that, the ball is going up. So I don't want to include that, but I do want to include this. And there you go. And I'm done. This right here is a motion diagram. It describes the motion of our falling ball. And what you'll notice is that the dots are very, very close together. But as the ball accelerates and the velocity increases, the dots get further and further apart. Also notice that, remember, since the time interval is fixed between all of these dots, the distance from this dot to dot, from this dot to this dot, is actually equal to the speed of the ball. If I actually pay attention to the direction, knowing that the ball went from here to here, well, that's actually a vector. Okay, that is actually a displacement vector. If I divide it by the time interval, it becomes a velocity vector, basically showing that the ball has traveled this distance down a particular direction. This distance in a certain amount of time will actually give you velocity. Nonetheless, this is what we're going to use, or at least this graphical representation right here is what we're going to use to answer the questions and to do the tasks that you are asked to do in your lab report. Now, as I mentioned before, we are only dealing with motion in one direct dimension. So we are not interested in the y dimension of motion. The x dimension of motion. We are interested in the y dimension of motion. So we will be interested in displacement, and we will also be interested in velocity, but not right now. So we're just going to stick with displacement. Now notice that your displacement basically behaves like a parabolic curve, which is what we would expect under the conditions of constant acceleration. So this actually does make sense to us, or when we actually have that lecture, it will begin to make sense to you. Now, if you'll bear with me, what I need to do is make a few changes so that we can actually see the lab report write-up. Okay, and here we are. Here I have our write-up. Here I have our graph. And also, when we need it, I also have a calculator. Okay, but we don't need that calculator right now, so we'll make it go away. So let's go on down to part B. So we have accessed our software, we have imported the photo, we have set the origin to where the object was just before it's dropped, made it so that the displacement is positive by having the y-axis point down, and we've created our motion diagrams. Okay, so the first thing that we're going to want to do is use the software to perform a quadratic fit for this particular graph. Now, how do you do that? You do that down here. Click this. We want to apply a curve fit. There it is. We don't want it to be linear. We want it to be quadratic. And there you go. And we'll go ahead and hit apply. And these are the parameters for our quadratic equation. Here is the quadratic coefficient, the linear coefficient, which we would have hoped would have been 0, but it's not, and our constant coefficient. And of course, we also have a root mean squared error, but we don't care about that. The primary thing that we care about is A. And it turns out that the acceleration is going to be twice that value. Okay? And 2 times 4.822 is 9.644. That is our estimated acceleration from this particular graph. So we want to note that, and we want to note that in table 1 of our report. So coming down here to table 1, there she blows, and here we want to put in 9.644, and we're going to stick with 3 significant digits. So let's go ahead and just do 9.64. 9.64. And there we go. That's our estimate. What other fun things that we do am I asking you to do here? I'm also asking you to basically plot the graph. Here it is, and the curve fit in the report. Okay, and that for us will be a relatively straightforward endeavor. What we want to do is use our screenshot capabilities of your computer. I know what they are for Windows. Don't necessarily know what they are for Mac. For Windows, you want to do Shift Start S. Everything will basically come dark, and then you can highlight what you want to add. And this is what you want to add. You want to add all of this right here. This is all you need to do. Okay. It's going to be copied to your clipboard. You can come down to the relevant section in your lab report, which is right here, and hit enter. Not hit enter, hit paste. And there it is. Now what you can also do here is make it a little bit smaller, because you want both graphs, because you have to do another graph. You want them both to be on one page. But this is primarily all that is expected of you for this particular graph, I believe. Like maybe we need to go back and check the message, check the other part of the write-up just to make sure. So let's go ahead and do that. So we've done that. What else do we need to do? We need to record the magnitude of our displacement. We record the acceleration, put that in table 1. Cool, we already did that one. And we need to record the magnitude of our displacement and place that in table 2 of our report. Now the magnitude of our displacement is going to be that value right there. And we can find it by just moving this little thing right here until that. Now notice what I did. I probably should show that a little bit better. Is I just went ahead and I clicked onto here, and I clicked on here, and this thing appeared. So I just want to bring this to the very last dot. I'm going to make this bigger so it's easier for me to see what's going on. Get you out of the way. Very last dot. There it is. And we have 11.571. That's the maximum. That is the maximum displacement. So let's come back to my right up here. We want to go to table 2 and put 11.5. Well, actually, we're going to stick to in this case 4 significant digits. No, we'll stick with 3. We'll stick with 3. So here we are going to put in. It shouldn't be there. 11.57 or 11.5. No, let's stick with 11.57. All right, so there we go. Now I believe that is everything that we need for step 7. Okay, in that case, what we're going to do is we're going to come back to our software, and we want to create the velocity versus time graph. So we're going to click here, change this to Y, velocity versus time, meters per second. There it is, and we want to get rid of this. We don't need this anymore. We can get rid of that. All right, and notice that this is a lot noisier than our displacement graph. And that might be troubling for you, but to a certain degree it does make sense, because this graph right here is the first order difference from this particular graph. And any operation involving a difference, involving a derivative, is always going to be a noisy operation, as opposed to an operation requiring the averaging of data, which will always be a lot smoother. So yeah, it is really kind of not behaving very well, but we're not going to let us concern that for the time being. Okay, so what do we need to do here? We need to apply a linear curve fit. Okay, so once again, come down here, apply curve fit, linear, hit apply. There you go. Okay, now for this one, we have a slope of 9.465. Okay, that slope is the rate of change in velocity or acceleration. This right here is the estimate of our acceleration. Now notice that this is this isn't units of meters per second squared. They kind of do it weird here. Here we have meters per second. Trust me, meters per second squared. Okay, so our estimate for acceleration is going to be 9.47 meters per second squared. The 5 rounds up. We're going to stick with 3 significant digits here, so that's going to round us up to 9.47. So what we can do is come down to, and we want to record that in table 1. That is right here, and that will give us 9.47. 9.47. And then what we're asked to do is to compute the percent difference. It's up there somewhere. And that's what we're going to do with these two values. Now this right here is the percent difference. It's going to be the absolute value of the difference divided by the average of the two times 100, which simplifies to this. And I'm going to do that on my calculator right here. So I'm going to have 9.64. Well, first off, parenthesis. No, 2 times parenthesis. Let's go ahead and use the larger one. 9.64 minus 9.47, close the parenthesis, divided by, open the parenthesis, 9.64 plus 9.47, close, times 100, and that is my percent error, 1.77%. I'm going to write that as 1.78%. All right, boom, done. What else do we need to do? So we did A, B, and C and D. We want to compute the integral between the curve and the x-axis. Now, it turns out, and we'll talk about that when the time comes, or you already have, depending on when you listen to this, that the area under this curve is going to be should be equal to the displacement of the ball. Okay, so that's what it should give us. So let's go ahead and compute that area. And we can do that with view integral. And there it is. Okay, and here our area is 11.667. And we want to record this in table 2. And let's record that as 11.67. And then once again, we can compute the percent difference. And the percent error, that's not really all that bad, is going to be 0.8605%. That will round up to 0.861%. And then what else do we have to do? Okay, well, we've done that in table 2. We compute the percent difference, and now we want to plot the graph and the curve fit on your report. If you want, you can plot the graph, the curve fit, and the integration on your report. Plotting the integration is not required. If you want to remove that, you are more than welcome to. And you can do that by basically just Xing out that box right here, and then the integral is gone. But this is, at the very least, I want to see this. To do this, we're going to do the exact same thing. Shift, Start, S, brings us our snipping tool. Go ahead and grab this. Make sure you include the y-axis there and the x-axis here in all of the data points. Let go. Come to the right spot, which would be right here, or which would be right here. Paste. Clean it up a little bit if you have to, and I think in this case we don't. There it is. And you are done with that. There's only one more thing that we have to do, and that is fill out table 3. Now, I don't have specific instructions in here, but clearly if it's there, there's something you need to do. So we want to compute the average of these two values, okay? And that average is going to be 9.64 plus 9.74 divided by 2. So that average is going to be 9.55, 9.56 when we round up. And now we are going to compute our percent error. Now this is this is what we measured. This is what it should have been, and would have, particularly in ideal situations. And so now we want to compute our percent error. Here's the formula for that. So that's going to be 9.81 minus 9.56. There you go. Divide that by 9.81. Multiply it by 100. And we have an error of 2.55%. Not bad if I say so myself. And once you've done that, then you are good to go. All you have to do, once you fill this out, well, there's two things you can do. One is you can fill it up by hand, print it, use your camera, whatever device you want, to scan it as a PDF and then submit it. Or what you can do is essentially put it in using put in your data using Microsoft Word. Come over here, delete all of this, and then this is what you can go ahead and submit into Canvas. You can just simply go to Canvas or go to the relevant page, hit Start Assignment, and here is where you can upload your file. Click Choose File, come to here, And there you go. Okay, so that's pretty much all there is to it. And I believe we are done here. If you guys have any questions, please feel free to contact me. You know how to get a hold of me. And this is Bob Boyle, and I am signing off.